from Rice University, who'll be talking about quantum symmetry. Sorry for it. This is going to be a very short introduction, Chelsea. I'm sorry.
Okay. My name is Chelsea Walton from Rice University. We'll be talking about quantum symmetry while Dave coughs up a lung. Should I start? All right. All right, well, thank y'all for coming. I know there are many Zoom seminars to choose from, and this might be Zoom hour number 5, 6, whatever for you today, so I appreciate your attention. If you have any questions, please just unmute yourself and ask, because I'm not good with manipulating the chat. So just go ahead and ask. So this is a talk about quantum symmetry. And in order to get started, what I need to tell you is, what is a symmetry? Well, symmetry is one of the oldest notions of mathematics. It appears in art, music, science, just about everywhere. But mathematically, what is a symmetry? So if we're given an object X, a symmetry of X is just a structure preserving transformation from the object to itself. And sometimes we want symmetries to even be invertible or reversible. Now, if we were to collect all the symmetries of a given object, it forms a nice algebraic structure, namely a monoid, given by taking two symmetries and composing them. That's your operation. And with the identity element being just leave the object alone. Now, if we were to collect all the symmetries that are invertible as well, then we get what's called a group, as we know. So here's some nice examples of symmetries of objects. We could take a parabola here with the symmetry, leave it alone and flip across the y-axis. That forms a group C2. We have this nice star here. We have the symmetry flipping across any axis you like, or even rotating by 2 pi over 5 radians. That gives you the dihedral group of order 10. And then you have this continuous object, I don't know, it's called a circle. You could flip across any axis, rotate by any degree, and get a nice infinite group. But in order to motivate the aspect of quantum symmetry that I'm going to talk about, namely the algebraic aspects of this field, what I want to do is tie this into symmetries of algebras. So the upshot is that symmetries of geometric objects, they go hand in hand with symmetries of function algebras or coordinate algebras on the objects. Now, this is best illustrated for symmetries of affine varieties. What's an affine variety? It's just some shape cut out by setting a bunch of polynomials equal to 0. So for example, this parabola here is an affine variety because you set the polynomial y minus x squared equal to 0. By the way, I'm always working over C. I'm not a fancy person. I don't mess with characteristic P too much, just C for now. Now, the group of symmetries again is Z2, but how does this relate to symmetries of algebras? Well, in this case, the coordinate algebra of this shape here is just the coordinate algebra of C2. In other words, the polynomial algebras in these coordinates x and y. And then we just force y equal to x squared by modding out by that ideal. And here, the symmetry given by a flip is just given by taking G, and it sends x to minus x and y to y. All right. So actions on affine varieties that correspond to actions on function algebras or coordinate algebras. Now let's get a little fancy and package this in the language of category theory. It's very nice bookkeeping. Now, what is a category? I mean, category is just a collection of objects and maps between them satisfying some very natural axioms. And what category theory allows us to do is translate information or information pertaining to objects and maps in one setting to objects and maps in a different setting. In particular, what I want to do is use category theory to talk about symmetries in the geometric side and translate it over to the algebraic side. Now, the way that's done, I'm going to take the category of affine varieties. We just talked about affine varieties before. And the corresponding algebraic object is a commutative algebra over C. And the way to get from one category to the next is to take an affine variety and take its coordinate algebra. And this is a contravariant functor, meaning that if I have arrows going in one direction in the left category, they go in the other direction in the right category. Okay. Now let's get a little saucy. Okay. Before I talked about a group action, but what does this mean categorically? So I have my object X here, and I'm going to have some group action on it that gives me some map going from G cross X to X. Now, X is an affine variety. All this business happens in the category of affine varieties. So G itself must be an affine variety. It must also be a group. So what this means is that there have to be some maps, operation map or a multiplication map, a map that plays a role of an identity, say sending a 1-point variety to the group, and also a map that plays a role of an inverse that satisfy group axioms. And these all must be maps of affine varieties. Okay, so that's what an action means geometrically over here. Now what I'm going to do is push this all over to the algebraic side. And what I end up getting is, well, from an action of a group on an object, I get a co-action of the coordinate ring of the group on the coordinate ring of the object. These are all commutative algebras. It's all in this category. So OG, it's a commutative algebra, but it also has some extra structure to it. G had some extra structure over on the geometric side, namely had these three maps. But now algebraically, they get pushed over here to giving us extra structure on this commutative algebra. Namely, O of G has a so-called co-multiplication, a co-unit, and an antipode. And what the compatibility axioms of these maps give us is that O of G is a so-called Hopf algebra. Okay, so just to sum up, classical symmetry of objects we can see. Geometrically, these are captured by group actions. Algebraically, they're really captured by coactions of commutative Hopf algebras. All right, any questions on this? Okay, we'll keep rocking and rolling, Okay, let's do some examples, make sure we're grounded in examples. If I take this, what's it called, parabola, parabola, I can look at its group symmetry, Z2 acting on it, and it corresponds to the coordinate ring of Z2, namely the polynomial ring in one variable modded out by the relation that defines the group, co-acting on the coordinate ring of the parabola. And the coaction is just given like so. Right, and here's the rest of the Hopf structure for this Hopf algebra here. I'm going to define what a Hopf algebra is later, don't worry. Just want some examples for now. Here's another interesting example that we'll come back to. We can take symmetries of a space, complex space. And as you can imagine, there are lots of different symmetries of it, so I have to narrow down. Let's leave the origin alone. Let's only consider linear symmetries, meaning sending lines to lines, not lines going off to some squiggle. And let's also take invertible symmetries. So when you collect all of these symmetries of this complex space together, you end up getting the group GL2C. These correspond to invertible 2x2 matrices. This is a perfectly fine group, but it's also an affine variety. It's defined by taking the determinant and forcing it to have an inverse. Okay, so it's an affine variety in this space. Now, group actions on this space, actions given in this form, correspond to coactions of the coordinate algebra, which is a commutative polynomial ring modded out by this relation here, coacting on the coordinate algebra of this space, the polynomial ring. And you can kind of see how the relation works. I have matrix multiplication, given the action over on the geometric side. You sort of have like a matrix co-multiplication over here. Okay. All right, so classic symmetries, particularly those that are invertible, controlled by group actions, and algebraically, they're controlled by coactions of commutative Hopf algebras. All right, so that's classic symmetry. What is quantum symmetry? This is not well defined. This is not well defined. There are lots of different flavors of this field. There's a whole semester at MSRI about this. I think a lot of us are trying to coalesce different versions of this field. There's an algebraic version, there's an analytic version. You could talk to Dave about this, topological flavors. And of course, this relates to quantum physics. But I would say the grand uniter of them all is category theory, which I won't get into. What I'm going to stick with in this story is the algebraic side. The basic philosophy is this. This is sort of my philosophy, what I think should be true. If you're given an object, the more sophisticated the object, the more sophisticated the framework you need in order to analyze or capture its symmetries. So let me explain why we need such a framework. Let's illustrate this for symmetries of quantum objects. Now, quantum objects, we can't visualize. That's why I have these funny pictures here. When I typed in quantum into Google, I mean, it gave me these GIFs. So it's kind of weird, but we can visualize, well, actually, no, we can't visualize a complex plane. We can sort of draw it in a way. But if we wanted to take a so-called Q deformation of it, this is kind of a wild gadget. We can't visualize it at all. So how do we handle symmetries of this? Well, the basic technique is that, okay, at least through the lens of quantum physics, we can't observe quantum objects, but in order to study their symmetries, what you can do is cook up a coordinate ring of the quantum object. Hello, cat. You can still study quantum objects through the use of their coordinate algebras, which are very concrete rings. All right, so before we want to study symmetries of these quantum planes, let's actually think of what their coordinate ring could be. Now, there are different models. Here's one model. If you take a complex plane, its coordinate algebra is a polynomial ring in two variables. And you can Q deform, and by Q deform, I mean take a non-zero scalar and sort of think of what a quantum plane could be by its Q version of a polynomial algebra. So instead of taking X and Y and forcing them to commute, you force them to Q commute. Okay, so this is one widely accepted model for understanding so-called quantized two-space. This is algebras found all over physics papers. I deal with a lot in noncommutative. We study in this space. All right, any questions so far? Make sure we're all on the same page.
Could you please repeat the last two sentences you said? I think I lost connection. I don't know if everyone else did.
Oh, okay. I tend to forget what I said. What did I say?
About the quantized two space.
Okay, yeah. So there are different types of coordinate rings that we can take to model quantized two space. Here's one of them, especially if you're dealing with Q deformations. Yep.
There was a question in the chat.
Okay.
So Rodika asks, what is a Q deformation?
Geometrically, that's kind of hard to sort out. Algebraically, let's just say roughly it's a ring where the ring is equal to the original one as a vector space, and you use a Q. You use the scalar Q here to define a new multiplication. So deformation in general of an algebra is a new algebra that has the same vector space structure, but a different multiplication. And we use the Q to give the new multiplication. Is that it? Okay.
Thank you.
All right. So back to symmetry. Whatever this is, this should commute with deformation. Symmetries should commute with deformation. So let's just try this out in the framework of group actions and see what happens, see what goes wrong. We take a nice commutative polynomial ring. Remember, that's the coordinate ring of the complex plane. If we Q-deform it, one algebra that we could use is this noncommutative algebra here, the Q polynomial algebra. Now let's collect all of the, or form a nice collection of linear symmetries of these algebras. For instance, I can take the linear symmetries that are invertible and preserve the origin. For the commutative polynomial algebra, well, I get the general linear group, nice big group of matrices. But if I were to take all of the symmetries of this algebra that are linear, meaning that they preserve the grading, that are invertible, and that leave the origin alone, well, it hops around. If I move Q even smoothly from the from 1. So if I take Q as 1, I get the group GL2C. But if I take Q as -1, then there's a very small subset of matrices that preserve this algebra in such a fashion. Namely, I can only use anti-diagonal and diagonal matrices. And as soon as you move from Q equal to plus or minus 1, I can only have diagonal actions. So this is weird. I take my polynomial algebra, I smoothly deform it by slowly changing the multiplication by using this value Q here. We recover the algebra by setting Q equal to 1. So this is all nice and continuous, but the symmetries hop around. So this is a bad framework for studying symmetries of such deformations. But if we widen the framework a bit, and use actions or coactions of Hopf algebras, this works. So let's take our polynomial algebra again, and instead of using group actions, let's use coactions of this coordinate ring of the group on the commutative algebra. Namely, we had this coaction that we discussed before. Now, what's nice is that when I Q-deform this polynomial algebra, well, so we have a Q version of this polynomial algebra here. There's also a Q version of this Hopf algebra here, so that we can even use the same coaction. This all matches up quite nicely. And as soon as we take Q equal to 1, it specializes back up to this classic picture. So we have a nice smooth transition going from a commutative algebra to a non-commutative algebra, and the symmetries that come along for the ride. So this is a very, very nice framework for symmetry using Hopf algebras instead of groups. Any questions?
Are you going to say any more about OQGL2C?
What do you want to know?
Maybe what the co-multiplication might be or something like that, or?
Oh, okay. Yeah, okay, so here it is as an algebra. The co-multiplication and co-unit are given by the same formula, and the antipode, you have to Q-deform as well. Yep. Yep. And it has very nice behavior. I mean, ring theoretically, homologically, they're very much alike, these two algebras, especially when Q is generic or not a root of unity. Yeah, or even a root of unity, they're still nice. Okay.
Thanks.
Yep. Okay, so here's a takeaway point. Group actions, they provide a nice framework for classic symmetry, like function algebras on objects that we can observe. Coactions of Hopf algebras, they provide a nice framework for quantum symmetry, like function algebras of quantized objects or objects we can't observe in the sense of quantum mechanics. So this is one reason why it's nice to work in a broader framework of symmetry. Okay, so now I want to tell you what a Hopf algebra is and why they're nice. Hopf algebras, these have appeared first in 1940s in algebraic topology and the study of algebraic groups in 1950s. And then they were studied in their own right in 1960s and 70s, especially by Sweetler. Sweetler wrote the first book on them. And then they really, really came onto the scene during the boom of quantum groups in the 1980s. They came again in another wave in mathematics and algebraic combinatorics. And nowadays they appear, well, in quantum symmetry. Hopf algebras all over the place. So they've appeared in mathematics in waves, first in topology though. But what are they? So it's a 6-tuple. First of all, you take a vector space, right? And then you want a multiplication map and a unit map so that this triple gives you an associative unidal algebra. Okay, so at the end of the day, a Hopf algebra is an algebra with some additional stuff. We also want a co-multiplication map, co-unit map, so that this triple gives us a co-associative, co-unidal, co-algebra. All right, it's basically the same thing as this gadget here, except you flip all the arrows in a different direction. Anytime you see a co, you flip the direction of the arrow. Now, whenever you have two structures and you want to form a bigger one, you need some compatibility. Just like for a ring, if you have two operations in addition and multiplication, the compatibility is that multiplication distributes over addition. So here's the compatibility between these two structures. The co-unit is multiplicative. The co-multiplication, or I'm sorry, the unit is co-multiplicative, meaning that if I go around this diagram, I get the same result as going around this path. Same thing here. And here's how the multiplication and co-multiplication intertwine with each other, meaning that if I go around this path, I get the same results if I go around this path. So with these compatibility conditions, I get that this 5-tuple here is a bialgebra. Now, if I add in this gadget called an antipode, which it basically plays a role of an inverse, I get what's called a Hopf algebra. Okay, so it's a very rich structure, as you can see. There's a lot of duality in this structure as well, and they appear all over mathematics. Now, why care? Well, they're nice, okay? I get paid to study them. They're very nice. They generalize groups, okay? They generalize groups. And they should, because I told you it's going to have something to do with quantum symmetry, and which is a generalization of classic symmetry, which involves groups. Okay, Hopf algebras generalize groups. Why? In two ways. First of all, if we take a finite group and we form its group algebra, then it's a Hopf algebra with this given structure. Here's how you co-multiply an element. Here's a co-unit for an element. And here's the antipode, just given by the inverse. This is a very nice example of a Hopf algebra. We fill in the structure. Another way that a Hopf algebra, or another way a Hopf algebra generalizes a group, is we can take an algebraic group, which is a group plus having the structure of an affine variety. So we know what the algebra structure is, what the coordinate ring of this variety is, but how is it a Hopf algebra? Well, the co-multiplication, co-unit, and antipode, this is just the pullback of the affine variety maps given by multiplication, your unit map, and your inversion map. Back in that, the picture that we had before, relating the category of affine varieties with commutative algebras. So Hopf algebras are nice generalizations of groups. They've also been intensively studied in their own right, despite actually containing the classification of groups. They're still studied. So this sort of falls into two tracks. At least for the finite dimensional Hopf algebras, are ones that have finite dimensional vector space dimension. You can study the ones that are so-called semi-simple, or you can study the Hopf algebras that are so-called pointed. Now, what are the semi-simple ones? These are the ones where all of the representations, or all the modules, can be written as a direct sum of simple modules. Basically, what this means is that if you take a a Hopf algebra and you study its modules, then you can break up the modules into nice, simple pieces and just study the pieces. This is a very pretty theory. And actually, a lot of techniques from group theory are used to study such Hopf algebras, like, extension theory. There's even like a Jordan-Holder theorem. I mean, there are lots of techniques from group theory to study these. In fact, folks have wondered if all semi-simple Hopf algebras can arise from groups through a series of constructions. Like, yeah, I don't know if that's actually been addressed, but most of your examples of semi-simple, at least all of your examples of semi-simple Hopf algebras come from groups in one way or another. Then there are the pointed ones. Now, these are Hopf algebras where all the simple H comodules are one-dimensional. And what's cool about this theory is that there are a lot of Lie theoretic techniques to study these Hopf algebras. In fact, even Cartan data is used to group them together. So examples of these are universal enveloping algebras of Lie algebras. And the third reason why Hopf algebras are cool is because if you were to take a collection of all of their modules or comodules, that category, that collection has a very nice structure. It forms a so-called monoidal category. Now, what is this? Basically, this is a category where you can take any two objects, stick them together and get a third object. And then you have something that plays the role of a one, just like a monoid. Now, if you take any old algebra you like, you've seen algebra walking down the street, and you take two modules from it and you take their tensor product, you're not necessarily going to get a tensor product, a module again. But you do get one when you take two modules from a Hopf algebra walking down the street. Okay, so if you have M and N, these are two H modules, then how is a tensor product an H module? Well, you use the co-multiplication to get it. Co-multiply, flip, and then act on M here, and then act on N here. And that's the rule. How is the one? How is this other structure? How is the one a module? Well, you use the co-unit here. Okay, so Hopf algebras have a very, very rich structure. Any questions so far? This is a crash course in Hopf algebras.
Is there any particular distinctive structure this tensor category of co-representations would have, or would you expect as coming from Hopf algebra?
Oh, is there any additional structure we get on this category? Oh, yeah.
Or property?
Okay. Yes, so it's monoidal, it's rigid, which I don't want to define, but it has duals. That the antipole gives you duals. Mm-hmm.
Okay, yeah, thank you. Fair enough.
No problem. Anything else? Okay. All right, so that's what we're going to act with. What does action mean? What does action mean? We know what a group action is. What is a Hopf algebra action? So if I have an algebra, it's a triple, a vector space with a multiplication mapping unit. What does it mean for a Hopf algebra to act or co-act on an algebra? Well, a fancy way of saying this is I have my monoidal category of modules or comodules, and I take an algebra object in it. Okay, that's the fancy way. But unpacking this is what this means. An algebra is a triple, object, two maps. And I want the object to be a module. I want the two maps to be module maps. That's it. I want everything to lie in this collection of modules. So examples of this, the polynomial ring of two variables that submits a coaction of this nice Hopf algebra. And so does the Q deformation. The Q deformation or Q polynomial ring emits a coaction of the Q version of this Hopf algebra as well. Okay, so that's what I mean by, well, a symmetry. Okay, any questions on this? because next I have to kind of convince you that I've done something. Yeah, usually I wait till the last 5 minutes, and I've had to stop doing that. Like story time, and then 5 minutes left. Oh yeah, prove something. But I'm moving that up this time. Yeah. Okay. Well, no questions. All right. Oh, here's one result. All right. Here's a basic question. If you have an algebra A, polynomial ring, Q polynomial ring, matrix algebra, any algebra you like. An algebra is just nothing but a vector space with a ring structure with a vector space, however you want to think of it. Do you need a Hopf algebra to capture its symmetries, or will groups suffice? To make this more precise, we say that an algebra emits no quantum symmetry if every action of a Hopf algebra on it must factor through essentially a group action, or must factor through a Hopf algebra that is co-commutative, meaning that if we apply the co-multiplication and flip across the tensor product, we recover the co-product. Now, the reason why this is essentially a group action, at least in the finite dimensional case, is that finite dimensional co-commutative Hopf algebras over C are group algebras. Okay, so we say that an algebra emits no quantum symmetry if every Hopf action must factor through something co-commutative or essentially a group action. There are nice classes of algebras that don't have any quantum symmetry. Here's one of them. So if I take a commutative domain, like a polynomial algebra, like the coordinate ring of any irreducible affine variety, which is the commutative domain, and I act with a semi-simple Hopf algebra that sort of behaves like a group in a way, I don't have any quantum symmetry. All such actions must factor through something that's basically a group algebra. And from there, there are also generalizations of this result or extensions of this result. You also get no quantum symmetry on various deformations of commutative domains, like Q polynomial ring and n variables, at least when Q is a non-rooted unity, Weil algebras, and rings of differential operators in general. In fact, if you have a finite dimensional Hopf algebra that acts on any of these deformations of commutative domains, then that action must factor through the action of a group. Okay, so this is these are occurrences of no quantum symmetry. So what this does is it provides a way of saying, okay, at least this is a roadblock. This is when you're dealing with these types of algebras, groups are enough. Yeah. Any questions on this? All right. So there are genuine quantum symmetries out there. Okay, so same question applies. If we have an algebra, do we actually need a Hopf algebra to capture its symmetries? Sometimes we do. So we say that an algebra emits genuine quantum symmetry if there is a Hopf action on it that does not factor through the action of something co-commutative, or does not factor through a group action. There actually exists some algebras out there where the Hopf action sticks. We stay in quantum land. Here's some examples of this. If I take a commutative domain, before I had semi-simple here and got no quantum symmetry. If I replace it now with pointed, remember that was the Lie theoretic counterpart to the story above, we get lots of examples of pointed Hopf actions on commutative domains. For instance, I could take a polynomial ring in one variable, very nice commutative domain, and I can act by not even a Q version. I could just take this UQSL2. So this is called the Frobenius-Lustig kernel, or it's a quantized enveloping algebra. Very Lie theoretic algebra that's pointed and finite dimensional as well. So this action, it doesn't factor through anything like a group. It stays in quantum land. Even though this algebra is classic, it's commutative. There are also funkier examples that are very combinatorial. I can take a so-called path algebra of a quiver. So what is a quiver? A quiver is just a directed graph and a path algebra on it. This is just an algebra that's generated by paths of the quiver, and you can multiply paths if they concatenate, and if they can't concatenate, then it's 0. Okay. So yeah, Ryan Kinzer and I, we wrote down some very concrete formulas for actions on path algebras given by, again, these quantized enveloping algebras. Okay, so very genuine quantum symmetries here. All right, and then most recently in joint work with Amri Elswald, who's at Iowa, she's a grad student, they also produced generalizations of this result as well. And then it's another family of interesting quantum symmetries. I can take these gadgets called Artin Shelter regular algebras. So these are quite nice. These are algebras that are they're not necessarily commutative. They're graded, meaning that, well, you can decompose the algebra like so. They're connected, meaning that the 0th piece is the ground field, but they behave homologically like commutative polynomial algebras. They have a finite global dimension, they have a Gorenstein condition, they have nice polynomial growth. They're basically like non-commutative polynomial rings. And we have lots of examples of finite dimensional Hopf algebras that act generally on these gadgets. Examples of one of these are these Q polynomial algebras. Okay. All right, any questions on this genuine quantum symmetry business? I feel like I'm going too fast. Any questions on this?
Can I ask another question?
Absolutely.
So perhaps for this, for quiver algebras, is there any obstruction, compatibility, or guarantee of existence of certain quantum symmetries in terms of, I'm not sure exactly how these are classified, or like, you know, if given, I don't know, like an older characteristic of your quiver, then you can rule out some possibilities of existence of.
Nothing like that yet. No, nothing like that. Yeah, no, we have kind of bare bones stuff. Like if we have a cycle, we can create an action, but yeah, nothing, no obstructions like that yet. Yeah.
Nice. Thank you.
Very explicit formulas. It would be nice if they were packaged in a nicer way. Any other questions? Okay, I'll keep going. All right, so here's another set of results. And actually this is, so that stuff I kind of did during my postdoc and beginning of tenure track. Now what I'm interested in are universal quantum symmetries. So every time I've given a talk on this stuff, people ask, yeah, so what's like the biggest Hopf algebra that acts or coacts? Is there like a Hopf automorphism group type of thing? And the answer is yes, and I can tell you what it is. So a few questions. What's the biggest Hopf algebra that's going to act or coact on a given algebra? Very natural question. Does such a Hopf algebra share properties with the algebra that it's acting or coacting on? It should. So for instance, if I take this very discrete picture here, lines, points, nothing continuous about it, and I take its collection of symmetries, I get a nice finite discrete group, okay? I mean, sure, the dihedral group does not, it's not exactly a star, but their behavior, it's both finite, okay? And if you have this nice continuous shape here, you have a nice continuous group here. So the collection of symmetries should somehow mimic the behavior of the gadget that is acting or co-acting on. And also, what about other frameworks of symmetry? I mean, we talked about how, we really need to think beyond group actions to get a handle on quantum symmetry and use Hopf actions. But what about the next level up? And the next level up, do those levels compare? And you can get really abstract with this stuff. I'll only take it one more level. Okay, but these are the types of questions I've been thinking about lately. You have some symmetries. Can we catch them all? Okay. All right, so let's think about this first question. What is the biggest Hopf algebra that can co-act on an algebra? Now for here, I really do need to use coactions. Coactions is a good framework. Actions, not so good for this question, coactions. So in other words, we have a map given like so for co-module. So this is a Hopf algebra OV. It's going to co-act on A, possibly with some additional conditions, like if A is graded, maybe you want the coaction to preserve the grading. Filter, maybe preserve the filtration, blah, blah, blah. So this is a Hopf algebra that's going to coact on A, so that for any other Hopf algebra that coacts on A, we get a unique Hopf map going from O of A to H, so that this diagram commutes. We call O of A the universal Hopf algebra that coacts on A. So it's constructed universally. And as you can imagine, these things can be huge, big structures. These were first developed by Manin, by the way, in 1988. So some examples, if we consider nice universal Hopf algebras or bialgebras that coact on the polynomial algebra, I mean, this is where you start picking up coordinate ring of the matrix algebra, coordinate ring of general linear space or special linear space, the ones that we were considering above. And some of the special conditions that we need perhaps are having invertibility here or invertible determinant, and maybe determinant, whatever that means, equal to 1. All right. Now, what's cool is that oftentimes these universal Hopf algebras, they deform quite nicely. So there's also, for any, if an algebra is a deformation of something nice, let's say like A is a deformation of a polynomial ring, for instance, the universal coactions come along for the ride. There's something universal that's going to deform as well. So there are GL-like Hopf algebras given like so. And so for this example here, there's a Q version of this Hopf algebra here, as well as Q versions for these Hopf algebras and bialgebras up here as well. Okay, so the main reference is due to Manin. Okay, so we talked about the case where n is 2. But what about them? I mean, yeah, so you can create them. So what? Well, do they even behave well? A lot of times, yes. A lot of times, yes. So there's a question that Manin posed in a paper to Arden, Shelter, and Tate back in 1991, that if you have an algebra with very nice properties, finite global dimension, nice growth, Kazul, very nice properties. If you cook up these universal gadgets, do they also possess the same properties? And Arden, Shelter, and Tate, they proved that question has a yes answer for actions on these types of algebras. But in general, this question's wide open. It's very hard too. I've gotten really, really stuck on this question. So oftentimes, yes, oftentimes the universal gadget does mirror the algebraic properties as the algebra that it coacts on, such as if the algebra is Noetherian, then usually its universal gadget is Noetherian as well, domain, nice growth, as well as homological features as well. Any questions? Okay. All right. So now the last question. Oh yeah, my philosophy again. Yeah, I have this GIF. There's a philosophy. The more sophisticated the object, the more sophisticated the framework we need to analyze its symmetries. I really think that's true. Now, what I'm curious about is, so in a literature, there are all these different generalizations of Hopf algebras. Weak Hopf algebras, quasi-Hopf algebras, weak quasi-Hopf algebra, all sorts of different versions. But what are they good for in the context of symmetry? They should be the symmetry of something, but what? So what I'm convinced of is that there's these gadgets called weak Hopf algebras. I believe that they're the symmetries of very nice algebras that we can get a handle on. So let's start off by, well, let's just recall that we've been considering symmetries of algebras like the commutative polynomial ring. Graded algebras where the 0th piece is just C, just the ground field C. But there are lots of graded algebras out there where the 0th piece is not equal to just C. It could be bigger, like a path algebra of a quiver. The 0th piece, it has dimension equal to the number of vertices of the quiver. Or you can take a direct sum of graded algebras. The 0th piece has dimension equal to the number of summands you take. And there are other nice examples of graded algebras that have a bigger base. So do we need to work with actions or coactions of something beyond Hopf algebras? And I believe so. So there's some recent work here where we use coactions or actions of so-called weak Hopf algebras to study symmetries of these algebras. I don't want to go into the technical details because I know that we're near the end of the talk, but basically these are like bialgebras in the sense where it has the underlying structure of an algebra, coalgebra, but now the compatibility is weaker. It's a weaker condition. And there's also a way of measuring how far this weak gadget is from their, well, original gadget by using a base. Okay. So yeah, this is what I've been interested in lately. In any case, I think this game is fun. Yeah, I really do. I've been having a lot of fun. This is Algebraic Quantum Symmetry. Thank you very much for listening. That's it. Okay.
Thanks so much, Chelsea. That was fabulous. Are there any questions? She gave us a lot of time to ask questions during the talk. I was actually saving a question till now because.
Oh no! I write 40-minute talks. Like, yeah, try to talk.
Yeah, my question was, so in the beginning you were talking about symmetry as you know, you can have a monoid of symmetry, and if you require them to be invertible, then you get a group of symmetries.
Mm-hmm.
And so then this idea of taking functions on it, then I get O of G, and now I have a Hopf algebra. What if I take a monoid and I get rid of that invertibility at the beginning, and then I try to play this the trade for the function spaces again?
You
Is
get
that
a bialgebra? You get a bialgebra.
right?
Let's see. Yeah. Scroll. Yep. So now, yeah, this is fun. Okay. Yeah, this S takes care of the invertibility. We get rid of it. This 5 tuple here is just a bialgebra. Mm-hmm.
Okay, excellent. Thank you.
Sometimes, yeah, these Hopf algebras are called quantum groups. Okay, sometimes people, they reserve quantum group for special Hopf algebra involving physics. But in my mind, quantum groups and Hopf algebras are one and the same. But for the same reason, sometimes people refer to bialgebras as quantum semigroups. Quantum semigroups. Yep. I guess they should be quantum monoids. They should be. Oh, they should be. Okay.
Any more questions for Chelsea?
I'm off the hook.
It was an absolutely lovely talk, Chelsea. It
Oh, thank you.
really just, yeah. Thank you so much again for
No
giving that.
problem.
I think, yes, another round of applause.
Thank you. All right.